Hello and welcome to our PowerPoint module for this week. We're going to be discussing bivariate analysis. So we've done univariate analysis. Next, this week we're doing bivariate analysis, and then later on we're going to do multivariate analysis. I do want to give you a quick reminder for this week. We do not have class on Wednesday. We will all be meeting on Friday and again working with SPSS. Our objectives for this week are to introduce bivariate analysis and types of bivariate statistical tests. You're going to do bivariate analysis in SPSS, and then I also want you to consider the types of bivariate analysis that you would use in your proposed research, because this would go into your research design for the proposal. I expect that this module will take about an hour. There are a lot of slides, but that's really because I want to give you as much discussion of bivariate analysis as possible in the module to really prepare us to get moving on Friday. Here are your deliverables for this week. You have the PowerPoint module that you're doing now. There are 4 questions to respond to on Inquire. That's due by Tuesday night as usual. You do have an assignment due this Friday. Your research design is due on Inquire. Please do let me know if you have any questions about the research design, or if you want to discuss the research design in office hours or another time. I know that there are many parts to the research design, which is why I hope that you've already started thinking about this and perhaps working through your research design for the proposal. Here's your opening question for this week. It's not about the bivariate analysis material specifically. Instead, I want you to reflect on how you're feeling about your research proposal assignment for this course. Are you unsure about anything at this point regarding your research questions or research design? How can I help? Okay, so pause the module here, go to Inquire to answer this opening question, and then return for the rest. We're talking about bivariate analysis this week, and as it sounds, bivariate analysis is the analysis of 2 variables at a time. Okay, so univariates 1, bivariates 2. The ultimate goal of bivariate analysis is to identify relationships between variables, right? We want to see how 2 variables that we have in our analysis correlate with one another. Or another way of saying that is, how do variables vary together? Okay, so for example, let's say we're looking at the association between, or correlation between, income and happiness. If there is a correlation between income and happiness, we would see income and happiness vary together. You might assume that an increase in income or higher income is correlated with higher levels of happiness. Okay, so these variables are varying together. There is one significant limitation of most bivariate analysis, right? Specifically, any bivariate analysis that's using observational data, which is most of it. We're not running a lot of experiments in the social sciences. So from bivariate analysis, we can establish correlations, but we cannot establish causality. We can make some inferences about cause if we have sufficient evidence, which we'll discuss a bit later, but we cannot establish causality, particularly from observational data and bivariate correlations. We are going to do a number of examples throughout this module and in class to demonstrate bivariate analysis. So what types of analysis we can use and what kinds of output, say from SPSS, we get when we run a bivariate test. Before we get into different types of bivariate analysis, I wanted to run through some terms. Some of this is familiar and some of this may be new. First, it's important to know what a variable is. And this is review. We've talked about variables in class in previous weeks. But to review, a variable is a measured attribute or characteristic that varies across cases in our sample, okay? Hence the root vary. So a variable is something that varies from case to case. There are different types of variables that we utilize in bivariate analysis. And this designation of independent or dependent variable, this is one that we are making, say based on some hypotheses we have or some theory that we're applying. We are going to have in bivariate analysis one independent variable and one dependent variable. Now the independent variable is the one that we're proposing has some impact on another variable, that is the dependent variable. Whereas the dependent variable depends on values of the independent variable. Okay, so dependent variable is the variable that that's value depends on the independent variable. Another way of naming these, we could consider our dependent variable to be our outcome variable, right? So this would be the outcome, whereas the independent variable would be the predictor. You'll notice here that even though I said correlation does not equal causation, the very language that we use to describe our variables does sort of imply causality, right? If we're saying that our dependent variable depends on our independent variable. We can talk more about this in class. I think whenever you are framing a research project, we think in cause and effect, right? We do. We think, okay, well, one factor is causing another. This is true, but I do also want you to notice that the kinds of tests that we're going to do, the kinds of tests for correlations, do not give us any definitive answer on causality or one variable causing another. While our language tends to operate in this very causal way, and the way we think about our research questions tends to be causal. So there's a balance we need to meet in our writing and in our analysis to make sure that we aren't just saying that there are causal relationships that don't exist. But I digress. The last couple of terms here I want you to know are correlation. This is the analysis of relationships between two variables. So two variables are correlated. That means that there is some relationship between them. A change in one variable leads to a change in another. Finally, the correlation coefficient is the number that represents the strength or the magnitude of the relationship between two variables. Okay? We're going to see examples of this in the next slides, and we're also going to actually calculate some correlation coefficients using SPSS in class. Now, just like with univariate analysis, there are multiple types of bivariate tests. So the question becomes, which bivariate test should you use? Just like with univariate analysis, we determine what kind of bivariate test we're going to use based on the kinds of variables or the types of variables that we have. And remember those different types of variables. We could have interval ratio variables. We could have nominal, dichotomous, and ordinal. In addition, I think this is what makes bivariate analysis a little more complicated. Because we're looking at two variables at once, we have to consider both the type of dependent variable and the type of independent variable that we have. Okay, then this means that there are many different types of bivariate analysis. There is a figure in the book that you'll actually see on the next slide that gives possible combinations of variables and what kinds of bivariate tests you would do. I also, and you'll see this later in the module, have created a kind of spreadsheet that breaks it down a bit further. I ask for this course that you just refer to these. Say if I ask you a question on an exam about what type of bivariate test you should use, well, refer to a table or refer to the book to determine which type of test that you use. I'm going to show you on the next slide the different types of tests. Here's an example at the bottom of this one. So if you are looking at the relationship between gender, which is a nominal variable, and college major, which is also nominal, you would produce a contingency table, and you would run a Kramer's V test, and then a chi-square test, which is actually a test that we're going to talk about in a future week. Okay, it is on the table, but we'll talk about what a chi-square test is and what it gives you in a future module. Okay? Okay, so here's the table that's in the book that breaks down which types of bivariate tests you would use given the dependent and independent variables that you have. So you see across the top, there's nominal, ordinal, interval ratio, and dichotomous, and then that first column, also nominal, ordinal, interval ratio, dichotomous. So you just find the cell where you have overlap for both of your variables. So if you were doing nominal and nominal, like the example in the previous slide, we would look at, for the rows, we would look at nominal, then for the columns, we'd look at nominal, and it says here that you would do a contingency table, a chi-square test, and Kramer's V. Okay? I'm going to break down a little bit further what these different types of tests are in the next few slides. But this again is a kind of cheat sheet for you if you want to know what kind of test you should use. The note at the bottom says, please don't be overwhelmed by all of these terms. We're about to go through some of these, and we'll get to some others later. Okay, so I don't expect that you know what all of these mean at this point, but I just wanted to show you the table that's in the book that you can help to identify what kinds of tests you should use. One common way to visualize a bivariate relationship is to create a contingency table. You also might hear this being referred to as a cross-tabulation. Same thing. We produce a contingency table when we want to show the bivariate relationship between two categorical variables, meaning when we have two variables that are some combination of dichotomous, nominal, or ordinal. Okay? We do not use a contingency table when we have an interval ratio variable because it would be a very big table and not very useful to us. At the bottom of the slide here, you do see an example of a contingency table. And this is showing that, this is looking at attitudes toward marijuana legalization and the generation of our respondent. And this is coming right out of SPSS. So I ran this in SPSS. This is the output that I got. And you see the two categories for marijuana being made legal, it's legal or not legal, and then you see the different generations across the top. And if we go to any cell with these values, that's showing us the number of participants in the GSS who responded legal or not legal within each generation. So, for example, if we look at Gen Z and which is ages 18 to 20, we see that 35 people in our sample said that marijuana should be made legal, and 15 said it should not be made legal. And then we can go across and we can look at millennials, Gen X, and so on. Right? So this is just giving us the number of cases in each cell, and then it's totaled on the bottom. For Gen Z, we have 35 legal, 15 not legal, and then the total there, 35 plus 15, is 50. Okay, so this is one example of a contingency table. I also want to show you an alternative way of displaying your contingency table. So the table at the top here is the same one that you saw in the previous slide. It has number of cases in each cell. The one on the bottom, using the same data, the same information, but here I had it calculate column percentages instead of number of cases in each cell. So we have, for Gen Z again, the number of cases are 35 for legal, 15 for not legal. If we change that into a percentage, we have 70% legal, 30% not legal. So it's just converting these number of cases into percentages that are totaled by column. Now, there are benefits to having the column percentages. It does allow us to make comparisons across these generations much more easily. This is actually something I'm going to have you practice doing for the content question on the next slide. Okay, here's your content question. Based on the two contingency tables on the previous slide, does it appear that attitudes toward legalizing marijuana differ across generations? Describe any patterns that you see. Which contingency table, the top one or the bottom one, was more useful for you when looking for patterns and why? Okay, so you are going to return to that previous slide just to look at these two tables and tell me what patterns you see and tell me which table was most helpful in getting you to identify those patterns. So you can pause the PowerPoint module here, answer that content question, and then return for the rest. Before we move to other types of bivariate analysis, here's the last slide on a contingency table. And this is my rule of thumb for when it's useful and when you'd want to produce a contingency table. So you'll see on the left side, it's the table showing you different combinations of variables that you might be testing. And then I have an additional column here that says contingency table, and it's yes, no, or sometimes. All right, so for nominal and nominal, for example, you would want to make a contingency table. That's a useful way of visualizing the associations that you have. Anything interval ratio, it's not going to be useful. So anytime you have any combination with an interval ratio variable, you're not going to make a contingency table. It would just be way too big. Now, you'll see a couple of sometimes here. That's for ordinal and ordinal, and dichotomous and ordinal. And the reason why I have sometimes here is because it really depends on the number of categories you have in your ordinal variables. Ordinal variables can get pretty big, and they can have a lot of categories. So if it's going to be cumbersome to have a contingency table, maybe you wouldn't make one. But I think in most cases for ordinal variables, we would have a contingency table. Okay, so this is just a rule of thumb, something for you to refer to when you're making a decision about whether or not a contingency table is appropriate for whatever example you're using. Let's move on to tests of correlation. Because contingency tables are one type of bivariate analysis, but we might want to go a step further, and we might want to test for the correlation between our two variables. Correlations, or testing correlations, enables us to identify the magnitude or the strength of the relationship between the two variables that we are testing. Correlation tests also come in handy, particularly when we're using interval ratio variables, because we don't want to create a contingency table for those. So this is another reason why these tests of correlation are helpful for us. You see three figures on the slide, and let's say here we're using two interval ratio variables. Okay, so for example, let's say we're looking at county level poverty, so the county level poverty rate and the drug-related mortality rate by county as well. So these would be two interval ratio variables at the county level, and we plot each observation for both county level poverty and drug-related mortality on a scatter plot. So that's what you see here. You see three different scatter plots, and each dot represents a different case, or in the example I just shared, a different county. Let's say we're looking at counties in Virginia. And then along the x-axis, so the horizontal axis, maybe we have the poverty rate, county level poverty, and on the y-axis, or the vertical axis, we have drug-related mortality rate. So we can make all these dots for all of our observations, and then the red line would be what we call our line of best fit. This is the line that shows the overall patterns that we see with all of these dots. Now this is a way of visualizing a correlation. We have three different types of correlations we might observe. We might see a positive correlation. So in the example I gave you, we'd probably think that there's a positive correlation between county level poverty and county level drug-related mortality. as county level poverty increases, drug-related mortality also increases. That would be a positive correlation. On the other hand, sometimes we see negative correlations. This is when an increase in our independent variable corresponds with a decrease in our dependent variable. For example, let's say we're still looking at county level poverty, but our dependent variable is average life expectancy. So as county level poverty increases, average life expectancy decreases. That's a negative correlation. Increase in one variable corresponds with a decrease in the other. And then finally, we might see no correlation at all, meaning there's no relationship between the two variables that we're testing. And that's what you see on the far right of this slide. So these are three types of correlations that we might see. And I wanted to start with a visual because I think this will help us to understand what correlation coefficients mean when we get to that in the next few slides. So let's talk about correlation coefficients. A correlation coefficient shows us the strength and often shows us the direction of the relationship between the two variables that we are studying. Correlation coefficients have a range of -1 to +1. And -1 would be a perfect negative relationship, which is what you see on the left side, the figure on the left side of this slide. That would be a perfect negative relationship. And +1 would be a perfect positive relationship, and that's what you see on the right side of this slide. And then everything in between represents a different, say, strength and direction of a correlation, okay? We actually never see perfect correlations, especially in the social sciences. So if you have a correlation of -1 or +1, there's probably something weird happening with your data. We never actually see this. That would mean that we could perfectly predict somebody's, let's say, going back to that previous example, we could perfectly predict county level drug-related mortality based on county level poverty. That just doesn't happen. There's a lot of other things at play. So we never actually see a perfect correlation. We usually see something in between. Now, if we have a correlation coefficient of 0, right, that's right in the middle, right between -1 and +1, that means we have no correlation at all, okay? So know those three kind of extremes, -1 being a perfect negative correlation, 0 being no correlation at all, and +1 being a perfect positive correlation. And that'll help you to figure out what you're observing when you get a correlation coefficient that lies somewhere in between those values. Okay, so we'll talk about what these correlation coefficients mean, how you would actually read and interpret them. Here's my rule of thumb for determining the strength of a correlation based on the correlation coefficient. Okay, like I said, you really never see perfect -1 or +1. Instead, you usually see something in between. If you have a correlation coefficient that is between 0.7 to 1, we would call that a strong correlation. And given that it's a positive value, that would also be a positive correlation. On the other hand, if you're between -0.7 and -1, that would be a strong negative correlation. If you're between 0.3 and 0.7, that would be a moderate correlation. If you're between 0.1 and 0.3, or -0.1, -0.3, that would be a weak correlation. I mean, there's something going on here, but it's not a very strong relationship. And then finally, if you're between 0 and 0.1 or 0 and -0.1, we consider that to be no correlation at all, so no relationship between the two variables that you're testing. This is just a rule of thumb for you to, have on hand when you're trying to determine the strength of a correlation that you test. So remember that I said the type of correlation test that you're going to use depends on the types of variables that you have, and that's for both the dependent and independent variable, right? So we need to know what types of variables we have in order to determine which specific test of correlation we use. Now, I am not going to ask you to know how these correlation coefficients are calculated by SPSS, but I do expect you to know which test to use in SPSS based on which types of variables you have. So let's go down the list here. We have 4 different specific tests of correlation that we can do in SPSS. The first is Pearson's R, and this is the test that you would use if you wanted to know the correlation between 2 interval ratio variables. Okay, so that's the first one we have here. Let's say you have some combination of ordinal, interval ratio, and dichotomous variables. In this case, you're not going to use Pearson's R. We need to use a different test of correlation that takes the types of variables that we have into account, and that would be Spearman's rho. Okay, Spearman's rho is the test of correlation you would use if you, for example, had 2 ordinal variables, or an ordinal and an interval ratio variable, or a dichotomous and ordinal variable, really any combination of these 3, except for when you have 2 variables that are both dichotomous. Then I'm going to skip to the bottom. You would use phi in order to test 2 dichotomous variables. Then finally, if you have any nominal variable, let's say you have a nominal variable and an ordinal variable, or you have 2 nominal variables, or nominal and interval ratio, nominal and dichotomous. This is when you would use what's called Cramer's V. And Cramer's V is different in part because, remember that I said nominal variables don't really have a direction, right? There isn't a hierarchy or a way that we could put these in order. So when that is the case, you're going to use Cramer's V. So nominal with any other kind of variable is Cramer's V. Okay? Again, I don't expect you to know how these are calculated. I want you to know which test to use for which variables you have. And I also want you to be able to interpret a correlation coefficient in terms of the strength of the correlation that you see. Here's the same table from the book that I showed you before. I wanted to return to this briefly to show you that the type of test of correlation you use is also within this table. So for example, with nominal and nominal, you're going to do Cramer's V. For ordinal and interval ratio, you're going to do Spearman's rho, and so on. Okay, so you do see here that you can use this same table in order to determine which types of tests you're going to do based on which types of variables you have. And here's the same thing shown a different way. So this is something that I put together, a spreadsheet that has the different types of variables that you have on the left side, and then the next column is the bivariate method that you would use to test for correlations. Then after that, you see the possible range of the coefficient. And this is actually something that I meant to bring up earlier, but forgot to. Remember that I said most of the time when we think about correlation coefficients, the range is -1 to +1, and we have a correlation coefficient that's somewhere in there. Now you'll notice that for Cramer's V, the range of the coefficient is actually 0 to 1, so there are no negative values for a correlation coefficient for a Cramer's V. The reason for that is our nominal variables don't have an order, right? And if we don't have an order, then what would a negative correlation mean? It's just telling us that the possible range is 0 to 1 and doesn't really tell us anything about the direction of the correlation, because one of our variables doesn't really have any direction, right? So for all Cramer's V tests, the possible range of the coefficient is 0 to 1. For Spearman's rho, Pearson's R, and phi, we have -1 to +1. And then the last thing you see on the far right here is whether or not you should include a contingency table for the bivariate analysis as well. Okay, so you can again use this as a cheat sheet, use this as a reference when you're trying to figure out which tests you would do. All right, here's your video question. We're using the same video series, the Research by Design series, for correlation and for testing for correlation in SPSS. For this video, I actually only want you to watch to 547, and that's because we're not going to be covering the rest of what he covers in the video in class. So just go up to 547 and you can stop there. Here's your question. After telling SPSS to run a correlation, you get a correlation matrix as output. Describe the correlation matrix. What information does a correlation matrix give you? Okay, so you can pause here, watch the video, answer the video question, and then return for the last couple of slides. Finally, here's your closing question for this week. What kind of bivariate analysis would you do for your proposed research? Be sure to, in your answer, distinguish between your dependent variable and your independent variable. Okay, so what types, and it could be more than one, right? Maybe you're going to do a contingency table and Cramer's V, for example. So tell me what types of bivariate analysis you would do. And once you have done that, you can return for the final slide in the module. Okay, that's it for the PowerPoint module for this week. I know this one was a little bit longer, but we do have a lot of information to discuss with bivariate analysis. Here's what you have coming up soon. This Friday, you have your research design due. If you have any questions, want to discuss your research design with me, please do let me know. For next week, you have 2 readings. One is to just review part of Breiman Chapter 15 for multivariate analysis. And then I also have a second reading for you. It's an Evans and colleagues article called Stressing Out the Poor. It's more conceptual, but we can think about the ways in which multivariate analysis operates in this reading. You don't have any assignments due next Friday, so pay attention to that research design that's coming up, and I will see you in class.